Welcome back to week 5. I hope you're all surviving the midterm season. So our own midterm, this class will come up on on Friday. I believe it was Friday. So for that, I want to make some announcements. So just to prepare you for the test. First of all, I think this question has come up before. If you use theorems from the lecture, and you can use everything that we did in the lecture, there's no need to actually use the numbers of the theorems. We don't know them ourselves. Like when we grade them, we don't know the numbers. But what is helpful is if you state the content of the theorem briefly. If you say, for example, by this theorem, it is sufficient to test these two things to a verified subspace. And then you just list those two things and then you use it. The most important theorems have number or have names even. So you could say by the reduced theorem, or you could say by the extent theorem, this and this follows. There's been an announcement by Sean on Quercus, so please go and read that. I think there's nothing more than what I'm saying, but just go ahead and read that too. The test will cover what we did from section 1.1 to 1.6 and 2.1, including everything that was on a homework or an assignment. So that might also appear in the test. There's a term test 1 information document. Please read that in advance so that you know what to do when the test is there. Don't procrastinate. I know that we all procrastinate all the time, but in this case, if you have problems uploading your solution or something, we can help you with that, but not last minute. So we expect you to, if you have questions, don't wait until the last minute. We will be monitoring our emails and Piazza. So if you have questions, you can reach us. Right, so the last 3 is nothing that should surprise you. But just as a general hint for test writing, take your time to read the question carefully. It's better to waste 5 minutes just reading one question than wasting 50 minutes solving the wrong question and then realizing, oh, that wasn't even the question. And this has happened to me before. So I think it had happened to all of us before. This also includes the difference between if and only if. If you need to prove if and only if, and you only prove if, then half of the proof is missing, literally. Same things with giving a proof, an explanation, or maybe just decide. Maybe it's true or false, or it's true or false with an explanation or a counterexample. So make sure that you read this carefully and slowly. For notational differences, I think I've mentioned before that we use for vectors this notation. But the book uses fat fonts without an arrow on top. And it might also happen that instead of having T of V with parentheses, it might also be written as just Tx. So this is the same. It means the same, T applied to a vector X. And of course, tomorrow, in the last hour of the lecture, we'll be going over the stuff that we did so far. I'll give you a quick review of everything that we had. But for now, let me continue in the material for this week and leave everything else, the review, to tomorrow. Are there any questions? Okay, so I noticed that we're kind of ahead of the other sections in this lecture. And this means that we can now focus a little bit more on details and maybe focus on quality over quantity. So if you had the feeling that this lecture was rushed, then please go ahead and ask more questions now and slow me down if you feel like I'm rushing over things. So by the end of this week, we're only going to get to section 2.3 or 2.4, and not to section 2.5, which I believe was scheduled in the syllabus. I've already defined kernel and image. And the latest homework question actually goes over the proof that the pre-image and the kernel, the pre-image and the image are vector spaces. And last time we went, this is not, this was last time. Last time we did go over some, did we go over some proof? Anyways, so I think I explained last time why the kernel is subspace. We also looked at examples. So I've copied them in these lecture notes as well, if you want to look at more examples. Okay, so what we're going to do today, and remember last time what we also did, I was telling you about this coordinate map gamma, so that whenever you have a vector space, with a basis alpha, then there are these two sides to it. So we can have concrete vectors and explicit vectors. But then there's this way that we can go over to a blueprint world, another realization of the same data. So there's nothing added or lost from the data to the n-tuple world. So this is the n-tuples in Rn. That's something that we spent a lot of time last week, where we explained how this gamma alpha works, that it's a transformation, it's even linear, and how it's used to send a vector v to gamma alpha of v, which we also wrote as the vector v in square brackets. That was the coefficients needed to express it in a basis. Okay, so then we also that was just the first part. What we also did was, if we have a transformation from v to w, where we have bases alpha of v and beta of w, we saw that this just corresponds to a matrix T alpha beta from Rn to Rm. And it sends an n v1 to vn to the matrix product. So this is the matrix Vn. This is the matrix which we called T alpha beta. And this can be found, and we did this last time explicitly, we found this matrix for transformation where we first had to fix alpha and beta. So I want you to think about this as a blueprint world, and this as the real world. These are not formal words, but everything that's formal, that's actual math words that you can use without embarrassing yourself. Okay, so let's move on, because now I've introduced new things, the kernel and the image. And the goal of today's class is to investigate these two spaces, subspaces, kernel and image, further. And this duality, going from left to right, from real to blueprint, helps us to actually compute the image and the kernel of transformations. I think it just went away because I forgot to plug in my laptop, basically. Is everything back to normal? Can you hear me?
Yeah, I think it's working again.
Oh, okay, I just got a heart attack because my laptop went black and the screen went just off. And okay, I never forgot to plug in the laptop. That's the first. Okay, where were we? So I just told you about these two versions to think about vector spaces upon fixing a basis. And so the first proposition that we're looking at today is from the book. It's 237. And notice that here I wrote things in black, blue, and red. The blue one is you can ignore. So the blue one is very precise. But it might be hard to understand, specifically because I'm using the word isomorphic. So just ignore that for now. The red one is a more elaborate explanation of that. So the red one is something that we can actually understand well, and it's very explicit. And the proposition in the book, of course, doesn't use any of these words, but the meaning is the same. So what does it say? Well, if we have a transformation between two vector spaces, the transformation is linear, and we have bases alpha and beta, then what this is saying that the kernel of T is basically the solution space of a homogeneous system of equations. So it says that, well, let's actually do look at the blue line. If you compute the matrix representing T, and we consider to it the system, the homogeneous system of equations with this as the coefficient matrix, then the solution space of this will be the kernel of T. And the reason that I have to use this this confusing word isomorphic is, well, basically they're the same, but to identify them, we need to use the coordinate map gamma. So this means that you can technically, for now, just ignore this, that the kernel T is the solution of homogeneous systems. Okay, in red, what does this mean exactly? So this means for every vector in the kernel, the coordinate tuple, which we can associate to it, the tuple, the n tuple representing it in the basis, solves the homogeneous system. So this is how the identification is done. If we have a vector, then its coordinate tuple is a solution to the homogeneous system. And if we have a solution to the homogeneous system, then we can go backwards and we can assemble the vector to this n tuple, and we get a vector in the kernel. Does everyone remember how this going backwards, how this thing works? Can someone maybe just tell me in words so that I know this is something you understand? So if you have a tuple S1 to Sn, how do you build this? What would this be? The basis alpha is given like this. What is the realization, the explicit vector of this n tuple? Remember that it's supposed to be inverse to taking the n tuple of a vector. It's inverse to taking the coefficients in this basis. So the inverse just means that we build a linear combination with the basis vectors, and we use these entries in the n tuple as coefficients. It's going to be S1 alpha 1 plus S2 alpha 2, and so on to Sn alpha n. So we can always, from a tuple, we can build an explicit vector by just combining the base elements with these exact coefficients. So this is why you can think of this as a blueprint for a vector. It's just the coefficients that are given to you, and to actually build a vector, it's like assembling an IKEA furniture. You just look at the blueprint at the S1 to Sn, you plug them in and you stick them together, and then you have the furniture piece. In this case, the vector. Okay, well, let me just explain the proof. Now that we've laid out everything so detailedly in the proposition, it's not actually hard to prove this. We basically need to prove these 2 points. Let me maybe call them A and B. Okay, so we start with A. So this means suppose V is in the kernel of T. What does this mean? Well, by definition, this means that T applied to V is 0. Now, this is the 0 vector in W. This is very important that the zeros in V and W are different. Now, in W, we have a basis. So we can write or we can just write in general vectors in W as coordinate m tuples. I always using implicit that V is n-dimensional and W is m-dimensional, but it doesn't really matter. It can be just any tuple. I'm just making sure that the n and m tuples don't have to be of the same length. And this also means that, well, the zero m tuple in the basis beta, the 0 n tuple is just the zero. The 0 vector just has just coordinates 0, 0, 0. But this means that T of V has coordinates in beta, which is exactly 0. And by construction, T alpha beta is the matrix that satisfies what was it, T times alpha beta multiplied with the coordinate n tuple of V is equal to the coordinate m tuple associated to beta. But as we know, as we just checked, because V is in the kernel, this is 0. And so we have, if you now look at this from a different angle, and if you just establish a new perspective on this, this last line literally means this means this tuple V1 to Vn of V is a solution to the homogeneous system of exactly this matrix T alpha beta. So I hope this demystifies a little bit what I said before. But okay, so the other way around, I'll leave as an exercise, and we can maybe you can fill this in and just go backwards. So let me just leave this. From everything that I've said so far on this page, and from everything that is set up in the question of the proposition, it is not hard to verify that if S is a solution, then indeed this vector we built here is in the kernel. So that's all you need to do for part B. Instead, I want to look at an example because I think examples might be more illuminating than abstract definitions. Before we move to an example, are there any questions? Are you guys all still following me? Okay, I hope you are. If not, please do interrupt because we have a bit of a lead against the other sections in this lecture. So we can afford right now to go into more detail and to actually discuss things. Speaking of discussion, I think I did not put too many discussions in this lecture today. Sorry about that. If I can think of one, I'll just make one up on the spot. But first of all, let's look at an example. So now we want to find the kernel of the evaluation map, evaluation at 2 for polynomials. This is one of the examples. So just to remind you how this works, if you have a polynomial p of x inside of actually let's only go to 2, p2 of r, then the evaluation at 2 takes this polynomial and just plugs in 2 for x, and this will be a real number. I mean, polynomials have values at each point, which is just a number. Okay, so well, I did tell you what the kernel is abstractly, but let's actually compute this in the light of the last proposition. So let's compute this in 2 bases. So we just pick bases alpha, which is 1 x and x squared of p2r. And I hope this isn't confusing, but I'll just put the basis 1, the basis beta, which just contains 1 of r. It just means that in real numbers, you don't need actually a basis. It's just 1 is just a basis. And then the first question, actually, yeah, let me do this as a discussion. So please discuss this for 2 or 3 minutes. I guess this discussion means think about this yourself. What is the evaluation? What is the matrix representing the evaluation map? So I'll give you 2 minutes to think about this, and then we'll discuss this. Oh, I saw that I didn't even look at the chat so far.
Professor, are you able to see the chat?
Yes, I'm just reading the chat. Yes. Only the second hour will be a review session. So I'll still say a little bit about the content in the first hour of this week, and then the second hour will be a review session. You can still send me particular questions or things to go over in the second hour by email. Otherwise, I'll just go over everything that I remember from the lecture so far, and that I think might be helpful. Okay, let's resume with this question. So can someone tell me what the matrix representing this is? Yes, exactly. So Jency said it's 1, 2, and 4. Just as a brief explanation, how did you get there? Can you tell us? Okay, I'll just say a few words. Well, we just apply evaluation to. Remember, this was the algorithm from last week. The algorithm one with steps 1, 2, and 3. Apply evaluation to each basis element. 1x squared, and express it in the basis beta. Well, in this case, the evaluation 1 is just 1, and 1 in the basis beta is 1. I wish I had fast copy and paste, but this will do. Okay, so now when we apply the evaluation at 2 map to the polynomial x, the monomial, then we just get 2. So we just plug in 2 for x. And well, the basis beta is not very interesting, it just gives us 2. Same for x squared, only that now we get 4. So this will be 4, and then we arrange these columns. Well, they're just very short columns today in matrix, or in a matrix, to a matrix. So we have 1, 2, and 4. Okay, so now now the proposition kicks in, because now we saw that the solution space to a homogeneous system of this matrix will exactly be our kernel. So this is the next step. Find the solutions to 1, 2, 4. What should I use here? X is kind of dangerous to use again. Let me use x1, x2, and x3. Okay, how do we solve this? Well, we would usually row reduce if this wasn't already a 1/3 matrix. So this step is optional. This is required for bigger matrices, but in this case not. And then we just identify that this is a leading one, and these are free variables. And so this means, I guess you've done that plenty of times in 223. Well, the general solution to this system is contains 2 parameters. So this means there are in particular 2 parameters. Let me call them S and T. So now the general solution, the vector x, not a monomial x, just be careful not to confuse these, will be st and minus 2s minus 4t. Is this correct? Does everyone agree? Okay, and then also, so this is the part where I didn't know how to actually present this properly, because Let me just say a few things, and then you might object because I didn't introduce them properly, but maybe it still makes sense. So now what does this mean? This means we have fundamental solutions. Well, I think this is a term that you use in 223, I hope. Maybe we can call this, let's call this vector u, -2, 1, and 0. Maybe let's call this u1 and u2, -4, 0, and 1. And from everything that we did so far in this lecture, we can say that this is the same. These form a basis of the subspace of solutions to AX equals 0. And this is the part where I find I'm skipping over a lot of things, but from everything that we did so far, I think you can understand and recover what I didn't say. So what this means in particular is that solutions of AX equals 0 this is a subspace in our Rm for A in MAT n, m R. So the solution space of a homogeneous system is a subspace. And from last week's content, we know, or maybe the week before, know that a subspace always has a basis. And so what you've been told in 223 about all these fundamental solutions, and that you can reach any solution of the system by just combining them, is just a white lie for saying, well, they are a basis. And if you have a basis of a space, you can find combinations in this basis for every vector in the subspace. And that's the honest answer. But that wasn't probably not given to you in 223. Okay, so now we have the kernel. We have the blueprint side of the kernel. We have the solution space to the system of equations. So this means by this proposition, what was the number again? 237. The kernel of evaluation at 2 is given by vectors of the form gamma alpha inverse of, oh boy, how do I write this now? S1, S2, S3. Well, S equals S1, S2, S3. Solves 1 to 4 x1, x2, x3 equals 0. And let me be more specific here. So this means gamma alpha inverse of S1, S2, S3. Well, actually, I was I already told you that the general solution looks like this. So I already told you that this is what I can plug in. It's minus 2s minus 4t, s, and t. So what we really need to do here is we need to look at the vectors coming from n tuples of this form. So this is minus 2s minus 4t, s, and t. And now once again, you can see explicitly how this is done. Well, the alpha is just the monomials 1, x, and x squared. So if I want to build a vector, a polynomial, with this data of the tuple, this blueprint data, then I just as coefficients inside of the linear combination of the monomials. So this is this value times 1 plus s times x plus t times x squared. And then specific elements. So this is just a general element in the kernel. We can, of course, also find explicit solution, by choosing values for s and t. Remember, these were just parameters. So for example, if they're both 1, then gamma alpha inverse of minus 6, 1, 1. Remember, minus 6, 1, 1 is a vector in the solution space of this homogeneous system. This is just minus 6 plus x squared is in the kernel of evaluation 2. Let me add a new page. And now, well, we do the sanity check. Indeed, if we have evaluation of 2 of minus 6 plus x squared, this is minus 6 plus 2 squared. This is 0. So this means it is indeed in the kernel of the evaluation map. Any questions so far? Yeah, I think this is pretty cool too. So let me go one step further, and this isn't very rigorous, but I think it helps you to understand why we already at this point, so I might as well tell you. Oh, remember the gamma is going between actual vectors on the one side and their n tuples, the coordinate n tuples on the right hand side. So whenever you see something like this, or like a vector with square brackets around it, or a gamma alpha applied to a vector, that's what I used to indicate when you take for a basis the coordinate expression. Okay, so here I told you that the fundamental solutions are basically they are a basis for the space of solutions. So we have a basis of this. Now I will probably put this in this lecture in these notes for tomorrow as a theorem, but let me give you like a preview of the theorem. So for now, it's just a fact, just a helpful fact which you can use. But it won't be important for the midterms, so don't worry about that. This is already past the coverage of the midterm, so this is way beyond 2.1, section 2.1. So gamma inverse, gamma alpha inverse of U1, gamma alpha inverse up to say UK for fundamental solutions, U1 to UK of T alpha beta X is equal to 0. This will be a basis of the kernel. Yes, so that's going to be probably a theorem at the end of this week, tomorrow. But we already at this point. So I wanted to just use this example to actually tell you about this too. So in this example, remember that -210 and -401 are fundamental solutions. And this means that, let me just call this P of x, which is -2 minus x, and Q of x, which is -4 minus x squared. Let me just move them next to each other. This forms a basis of the kernel of the evaluation at 2 map. Yeah, all that I've done is I just use these coefficients to build actual polynomials in its basis. Okay, this is more than I wanted to say in this example, but I guess it just all fitted together nicely. Any questions? Oh, so k will be the dimension of the kernel. Because, I mean, the kernel technically be a subset of any dimension. So it could be 0 dimensional. It could just contain 0. It could be the whole space. If you have the 0 map, the transformation that sends everything in a vector space to 0, then literally everything is. So, yeah, exactly. Oh, we just pressed something on the keyboard. Okay, so there's a few more things I want to tell you today in the remaining 6 minutes. Because so now that we've done all this these shenanigans with the kernel, well, there's something analogous to the image. And again, I could, for the setup of a transformation T between 2 vector spaces which both have a basis, I could tell you in the blue font and the blue in the blue writing here. I could tell you very concisely, but very abstractly, that the subspace image is isomorphic to something, to some space associated in the blueprint world. But let's just ignore this for now, and let's look at the red writing. So it means that when the vector is in the image, then this corresponds to writing T of x. So this means that for some vector in V, W is equal to the image of V under T. So this W gets hit by some vector under this transformation. But this just means, in other words, if you look at the coordinate side, it just means that that in coordinates, T of V is just actually I'm already halfway proving this. So let me write this down properly. So if W is in the image of V, then for some V in V, W is the image of V under T. But this just means that the coordinate expression of W will be the coordinate expression of T of V. But now comes the definition of the matrix representing T is exactly built in a way that this matrix times the coordinate vector of V is equal to the coordinate vector of T of V. So this means that for every W in this image, this system, which is just W, is equal to T times something as a solution. And I'm kind of giving away the discussion here, but well, not quite. This is a solution to T alpha beta. Just any X is equal to B. Usually that's a B, the constant vector. And in this case, it's the, the coordinate vector of the W. And the other way around is also very similar. Let me not say anything about that. It's same way as before. If you have a coordinate vector of this kind, then you just apply the gamma inverse. The version of the red writing should be in GitHub. I'll also put this on Quarkus later, but I was running late in time. I was procrastinating the thing that you should do tomorrow, and then yeah, I haven't had time to put this on Quarkus yet. Okay, so the discussion you can do later. I want to get to one point by the end of today, which is this page. Right. So now before we go further and trying to apply this, I mean, obviously we've done very extensively the kernel, and we've done a computation very detailedly to find the kernel of something. Of course, now the same has to be done for the image. And to set this up, to set up the language for this, I want to introduce a few things that will make it easier to communicate what I'm going to say probably tomorrow. The first definition is when we have a matrix with columns A1 to AN. And I think I didn't want to write commas here, so ignore the commas. Just means that A is made up from columns, and I call the columns A1 to AN. Then the column space of A, this is the thing that I'm defining here, is just the span of its columns. So if I have the column space of a matrix 1, 2, 3, 4, then I just want to define this to be the span of the vectors 1, 2, and 3, 4. Okay, and now this lemma is probably the last thing I can tell you today about, but this is a good stopping point. So if you have a matrix which is given by columns, then the system AX equals B has a solution if and only if B is in the column space. And again, the proof isn't really difficult. It's more a matter of perspective. So you have to have the right perspective on what's going on here. The A times X, what is that actually? So given the matrix, and of course, X has to be an n tuple. So this multiplication, the A times X is well defined for X in Rn. You have to have matching numbers here and here. Otherwise, the vector is otherwise too long or too short. Okay, so if you have such a vector, then the product A times X, which can be written as A1 times X1 plus A2 times X2 and so on, n times x2, the matrix times vector product is the same as the linear combination of columns of A with the coefficients are the entries of X. And here I just mean the matrix times vector product, whoops, A times X. So notice, I mean, you can do an example of this. The nice thing to notice, like this lemma just basically tells you, look at the product of matrix times vector differently. Look at it where the vector just creates a linear combination of the columns of A. And then I need to say one more thing to actually explain the statement of this this proposition. So that's the first thing. And then the second thing is AX E. I don't know, I should probably write in a different. So now it is clear that, well, B inside. So AX equals B has a solution if and only if B is equal to some product A times X that is equal to some linear combination A1 to some linear combination of the columns of A. And now this just means this is equivalent with saying that B is an element in the space of all linear combinations. This is just the span of A1 to AN. And that's the end of the proof. Okay, so I'll leave you with this today, and tomorrow we'll just use this to compute the image explicitly in the coordinate world. I think there was one question. So the number of solutions will depend on the rank of A and the number of, so it will depend on the rank of A, the number of leading ones in the zero echelon form, and also on M. So it will be M minus the rank of A. That's the same old theorem saying that a solution of a system AXB, which is consistent. And here, well, basically we're saying that this is true. This also just means that the system is consistent. That's the same meaning. The number of parameters in a solution is equal to the number of variables minus the rank. That's something you've learned last semester. Okay, that's the end of the lecture for today. Thanks for your attention, and I'll upload the video later. Any questions?
Hello, Professor.
Yes, hello.
Are you able to go up to the proof that you did for the observation? Yeah,
This
that
one?
Yeah.
Yeah.
All right, thank you so much.
Sure. Funnily enough, this observation is not in the book as I couldn't find it. So there's no proposition that is analogous to 237 in the book. But I think it's just the obvious thing to state here.